On December 25, 2021, humanity launched the most powerful telescope ever built into space, the James Webb Space Telescope, a $10 billion engineering marvel with a mirror 6.5 meters across, designed to peer deeper into space and time than any instrument in history. Its mission? To observe the first galaxies that formed after the Big Bang, to see the universe as it was 13 billion years ago, when the cosmos was still an infant. What it found changed everything. In its first year of operation, JWST detected galaxies that shouldn't exist. Massive, mature, spiral galaxies with billions of stars, fully formed just 300 million years after the Big Bang. According to our best cosmological models, these galaxies are impossible. There wasn't enough time for them to form. The universe was too young, too hot, too chaotic. And yet, there they are, crystal clear in JWST's infrared images. Undeniable, real, impossible. Dr. Joel Leah from Penn State, analyzing the data, said it plainly. These galaxies are so massive that they conflict with 99% of our models for galaxy formation. If even one of these galaxies is real, it breaks cosmology. They're all real. JWST didn't just see farther than we've seen before. It revealed that the universe is fundamentally different from what we thought. Larger, older, stranger, and far more complex than our theories predicted. Today, we journey through the evidence that's forcing physicists to question everything we know about the Big Bang, dark matter, cosmic inflation, and the ultimate nature of reality itself. What you're about to discover will transform your understanding of existence, time, and humanity's place in an impossibly vast cosmos. The James Webb Space Telescope took 30 years to build. Development began in 1996 under NASA, with contributions from the European Space Agency and the Canadian Space Agency. The original budget, $500 million. The original launch date, 2007. Reality proved more complex. Building a telescope capable of observing the earliest universe required solving problems that had never been solved before. Challenge 1. The mirror. To see faint, ancient galaxies, JWST needed a mirror much larger than any that could fit inside a rocket. The solution? 18 hexagonal beryllium segments coated in gold, folding like origami for launch, then unfurling in space with nanometer precision. Each segment weighs 20 kilograms and measures 1.32 meters across. Together, they form a 6.5-meter primary mirror with a collecting area of 25.4 square meters, more than 6 times larger than Hubble's. Challenge 2. Infrared vision. Ancient galaxies are redshifted by cosmic expansion. Their light, originally emitted as ultraviolet and visible wavelengths, has been stretched by the expansion of space itself into the infrared. To see this light, JWST operates entirely in infrared, wavelengths invisible to human eyes and absorbed by Earth's atmosphere. But infrared detection requires extreme cold. Any heat generates infrared noise that would drown out the faint signals from distant galaxies. The solution? A tennis court-sized sunshield with 5 layers, each thinner than a human hair, keeping the telescope at negative 233 degrees Celsius, 40 Kelvin, just 40 degrees above absolute zero. Challenge 3. The location. JWST doesn't orbit Earth. It orbits the Sun, 1.5 million kilometers from Earth, at a point called Lagrange Point 2, L2. At L2, Earth and Sun align, allowing the sun shield to block both simultaneously. The telescope remains perpetually in Earth's shadow, cold and stable. But L2 is 4 times farther than the Moon. If something breaks, no repair mission is possible. JWST had to work perfectly on the first try. On July 12, 2022, NASA released JWST's first deep field image. The image showed a small patch of sky, roughly the size of a grain of sand held at arm's length, containing thousands of galaxies stretching back 13 billion years. Every galaxy in the image was farther, older, and more detailed than anything Hubble had ever captured. But that wasn't the shocking part. Dr. Ivo Lab from Swinburne University began analyzing the spectra, the detailed breakdown of light that reveals a galaxy's age, distance, and composition. What he found made no sense. Several galaxies showed spectral signatures indicating they formed just 300 to 500 million years after the Big Bang. That alone was exciting. We'd never directly observed such early galaxies before. But when Lab calculated their masses, something was wrong. These weren't small proto-galaxies slowly assembling from gas clouds. They were massive spiral galaxies, some containing 100 billion stars, as massive as the modern Milky Way. In February 2023, Lab published his findings. The 6 candidate massive galaxies we've detected at 500 to 700 million years after the Big Bang are far more massive than expected. If spectroscopically confirmed, they challenge the hierarchical formation model that has been the standard for decades. The hierarchical model predicts galaxies form gradually. Small clumps of dark matter attract gas, gas forms stars, small galaxies merge into larger ones over billions of years. The early universe should contain only small, primitive, irregular galaxies, not massive, mature spirals with defined structures. Yet, that's exactly what JWST saw. By mid-2023, more observations confirmed the pattern. JWST 4590, a galaxy observed at redshift Z equals 10.38, appears to have formed just 480 million years after the Big Bang. Its stellar mass, approximately 100 billion solar masses. According to standard models, forming that much stellar mass requires at least 2 to 3 billion years. The universe at that epoch was only 480 million years old. The math doesn't work. Dr. Mipe Boylan-Colchin from the University of Texas ran simulations using standard cosmological parameters, the Lambda-CDM model that has successfully explained cosmic microwave background radiation, galaxy clustering, and large-scale structure. His conclusion: to form these galaxies so early, star formation efficiency would need to be 2 to 3 times higher than theoretically possible. Either our distance measurements are wrong, our mass estimates are wrong, or our understanding of galaxy formation is fundamentally incomplete. Follow-up spectroscopy confirmed the distances. The redshifts are real. These galaxies are as far away and therefore as ancient as they appear. Mass estimates were double-checked using multiple methods. The galaxies are genuinely massive. That leaves the third option. Our theories are wrong. Dr. Stacy McGaugh from Case Western put it bluntly, JWST is showing us a universe we didn't expect. The galaxies are too big, too mature, too organized. If this holds up, we're going to need new physics. Let's be specific about what makes JWST so revolutionary. Sensitivity. JWST can detect objects 100 times fainter than Hubble. This isn't just incrementally better, it's transformative. Galaxies invisible to every previous telescope are crystal clear to JWST. Infrared range. JWST operates from 0.6 to 28.5 micrometers, wavelengths where the most ancient and distant objects shine brightest due to cosmological redshift. Spectroscopy. JWST doesn't just take pictures, it breaks light into spectra, revealing precise distances, compositions, temperatures, and ages of galaxies billions of light-years away. Resolution. JWST's angular resolution in infrared is comparable to Hubble's in visible light. We're not seeing blurry blobs, we're seeing detailed structures in galaxies that formed when the universe was 2% its current age. And what it's revealing is systematically different from predictions. Not just a few anomalies, not just measurement errors, a consistent pattern. The early universe was far more evolved than it should have been. Galaxies formed faster, stars formed more efficiently, structure emerged earlier, and the implications extend far beyond galaxy formation into the fundamental nature of the cosmos itself. But the evidence forces us to confront an uncomfortable possibility. What if the universe is older, larger, or fundamentally different than we've believed? In July 2023, astronomers using JWST discovered CEERS 93316, a galaxy candidate at redshift Z equals 16.7. If confirmed, this galaxy formed just 250 million years after the Big Bang. But here's what's shocking. It contains heavy elements. Stars create heavy elements, anything heavier than helium, through nuclear fusion. When massive stars explode as supernovae, they scatter these elements into space, enriching the next generation of stars. This process takes time, hundreds of millions of years for multiple generations of stars to form, live, and die. CEERS 93316's spectrum shows carbon, oxygen, and iron. That means it's not first-generation stars. It's at least third or fourth generation. But the universe at 250 million years old should only contain first-generation stars. Massive, pure hydrogen and helium, no heavy elements. Dr. Tommaso True from UCLA noted, "Finding heavy elements this early is like finding a teenager in a nursery. The timeline doesn't make sense." Galaxies evolve through stages. Young galaxies are typically irregular, chaotic blobs of gas and stars with no defined structure. Over billions of years, through mergers and gravitational interactions, they settle into organized shapes, spirals with defined arms, ellipticals with smooth distributions, barred spirals with central structures. Hubble observations showed this progression clearly. Early universe galaxies, 1 to 2 billion years after Big Bang, are mostly irregular. Modern galaxies, 13.8 billion years after Big Bang, are mostly organized. JWST broke this pattern. Galaxy JADES GS-Z13-0, observed at redshift Z equals 13.2, just 325 million years after Big Bang, shows clear spiral structure, defined arms, a central bulge, rotation patterns consistent with an organized disk. Dr. Hannah Ubler from Cambridge analyzed its kinematics. This galaxy has a rotation velocity of 250 kilometers per second and a well-defined disk. It's indistinguishable from spiral galaxies in the modern universe, except it formed 13.4 billion years ago. How does a galaxy develop organized structure in just 325 million years when simulations suggest it requires 2 to 3 billion years? Nobody knows. Dark matter is supposed to be the scaffolding of the universe. Standard cosmology predicts that after the Big Bang, dark matter clumped together first, creating gravitational wells where normal matter accumulated to form stars and galaxies. Galaxy formation should follow dark matter distribution. Where dark matter is dense, galaxies form quickly. Where it's sparse, galaxies form slowly. JWST observations challenge this. Some regions of the early universe show abundant massive galaxies with no corresponding dark matter overdensity, as measured by gravitational lensing effects. Other regions show dark matter concentrations with surprisingly few galaxies. Dr. Priyamvada Natarajan from Yale, the correlation between dark matter and galaxy formation that we see in the modern universe doesn't seem to hold in the first billion years. Either dark matter behaved differently in the early universe, or our models of how galaxies form in dark matter halos are incomplete. At the center of most galaxies sits a supermassive black hole, millions to billions of times the sun's mass. These black holes grow slowly. They start as stellar mass black holes formed from collapsing stars and gradually accumulate mass through accretion and mergers. Growing a billion solar mass black hole should take billions of years. JWST discovered quasar J0313-1806, powered by a black hole containing 1.6 billion solar masses, existing just 670 million years after the Big Bang. That's not enough time for any known growth mechanism to produce such a massive black hole. Dr. Xiaohui Fan from the University of Arizona, this black hole had to grow at the maximum possible rate for its entire existence, accreting matter at the Eddington limit continuously. Any interruption, and it couldn't reach this mass so quickly. But continuous Eddington-limited accretion is considered physically impossible. Black holes periodically blow away their fuel supply through radiation pressure. The black hole shouldn't exist. Yet, it does. But this represents just one piece of a much larger puzzle hidden in the fabric of space-time itself. For decades, astronomers have measured the universe's expansion rate, the Hubble constant, using two independent methods. Method 1, observe the cosmic microwave background, light from 380,000 years after Big Bang, and calculate expansion rate from cosmological models. Result: 67.4 kilometers per second per megaparsec. Method 2 measured distances to nearby galaxies using standard candles, Cepheid variables, supernovae, and calculate expansion rate directly. Result: 73.0 kilometers per second per megaparsec. These values should match. They don't. The discrepancy is called the Hubble tension. JWST made it worse. In 2023, JWST measured Cepheid variables in galaxies up to 130 million light-years away with unprecedented precision. The result confirmed the higher value, 73.0 plus or minus 1.0 kilometers per second per megaparsec. The tension isn't measurement error, it's real. What this means, either our understanding of the early universe, derived from CMB observations, is wrong, or our understanding of local measurements is wrong, or the universe's expansion rate has changed in ways we don't understand. Dr. Adam Rees from Johns Hopkins, Nobel laureate for discovering dark energy, said, "The Hubble tension is now at 5 sigma significance. In particle physics, 5 sigma is the threshold for claiming a discovery. We've discovered that something is fundamentally wrong with our cosmological model." The first stars in the universe, population 3 stars, should have been massive, short-lived, and composed purely of hydrogen and helium. They should have formed in the first 100 to 200 million years after the Big Bang, lived a few million years, then exploded as supernovae, enriching the universe with heavy elements. JWST was designed to find them. They should be visible as extremely distant, extremely blue, metal-free objects. We haven't found any. Instead, JWST finds galaxies with heavy element abundances even at the earliest epochs it can observe. This suggests either population 3 stars formed even earlier than 200 million years, but the universe was too hot, population 3 stars were so efficient at creating heavy elements that even first galaxies show metal enrichment, or our models of primordial star formation are completely wrong. Dr. Volker Braun from the University of Texas, JWST should have found POP3 stars by now. The fact that we haven't is deeply puzzling. Either they're rarer than predicted, or they never existed in the form we imagined. Galaxies aren't randomly distributed. They cluster along filaments of dark matter, the cosmic web, a vast network of structures threading through space. Simulations predict this web takes billions of years to form, as tiny density fluctuations from the Big Bang slowly grow under gravity. JWST observed the cosmic web at z equals 8.5 when the universe was just 600 million years old. The web was already there, fully formed, with galaxies clustered along filaments in patterns identical to the modern universe. Dr. Charlotte Mason from the University of Copenhagen, the large-scale structure we're seeing at z equals 8 is far more evolved than simulations predict. It's as if someone hit fast forward on cosmic evolution. This has profound implications for our understanding of cosmic inflation, the rapid expansion in the first fraction of a second after the Big Bang that's supposed to set initial conditions for structure formation. If structures formed too quickly, maybe inflation worked differently than we think. Or maybe there was additional physics in the early universe accelerating structure growth. Here's something subtle but deeply strange. Early galaxies are too well-behaved. When Hubble observed galaxies at redshift z equals 2, about 3 billion years after Big Bang, they were chaotic, irregular shapes, lots of mergers, significant clumps of star formations scattered throughout. Theory predicts even more chaos at z equals 6 to 10, when the universe was less than 1 billion years old. JWST shows the opposite. Many early galaxies are surprisingly regular: smooth light distributions, organized structures, rotation curves that follow neat mathematical patterns. Dr. Erica Nelson from the University of Colorado analyzed dozens of JWST galaxies and found something unexpected. The average ellipticity, how oval versus circular galaxies are, doesn't change much from z equals 10 to z equals 2. Early galaxies are almost as organized as later ones. This is backwards. Chaos should decrease over time as galaxies settle. Instead, galaxies appear to start organized. It's as if the universe knew what it was doing from the beginning. The evidence extends beyond unexpected observations into the realm of fundamental cosmology itself. Let's establish what we thought we knew. The Lambda-CDM model, lambda cold dark matter, has been the standard cosmological model since the 1990s. It successfully explains the cosmic microwave background radiation patterns, the abundance of light elements, hydrogen, helium, lithium, the large-scale distribution of galaxies, the accelerating expansion of the universe. Lambda-CDM makes specific predictions about early galaxy formation. Timeline. First stars form 100 to 200 million years after Big Bang. First small galaxies form 400 to 600 million years. Galaxies merge and grow 1 to 3 billion years. Mature spiral or elliptical galaxies 5+ billion years. Mass growth. Galaxies grow hierarchically, small to large over time. Dark matter halos form first, then collect gas that forms stars. Star formation efficiency peaks around 10 billion years after the Big Bang. Early galaxies should be small, 1 to 10 billion solar masses maximum. JWST observations violate almost every prediction. Cosmologists are scrambling to explain JWST's observations. Several hypotheses have emerged. Hypothesis 1. Early dark energy. Maybe dark energy, the mysterious force accelerating cosmic expansion, was stronger in the early universe. This could have accelerated structure formation, allowing galaxies to form faster. Dr. Mark Kamiankowski from Johns Hopkins has developed models where dark energy strength varied over time. Early dark energy could speed up the collapse of matter into galaxies. But this requires rewriting fundamental physics. Dark energy is supposed to be a property of empty space itself, the cosmological constant. Constants don't change. Hypothesis 2. Modified initial conditions. Maybe cosmic inflation, the rapid expansion in the first 10 to the minus 32 seconds, produced different initial conditions than we assumed. Standard inflation predicts small Gaussian distributed density fluctuations, but maybe inflation produced larger fluctuations in certain regions, creating seeds for early galaxy formation. Dr. Paul Steinhardt from Princeton notes, if inflation produced a different spectrum of fluctuations than we thought, it could explain accelerated structure formation. Hypothesis 3. Primordial black holes. What if the universe contained more primordial black holes than we think? These black holes, formed in the first seconds after the Big Bang, could have seeded early galaxy formation and grown rapidly into supermassive black holes JWST observes. This bypasses the time problem for black hole growth. They start massive rather than growing from stellar remnants. Hypothesis 4. We're measuring masses wrong. Some scientists suggest JWST's mass estimates might be inflated. Maybe what looks like stellar mass is actually something else. Active star formation glowing so brightly it mimics a larger stellar population. But spectroscopic analysis suggests these are indeed mature stellar populations, not just young, bright stars. This forces us to reconsider fundamental assumptions about the Big Bang, cosmic evolution, and the nature of dark matter and dark energy. Dr. Alison Kirkpatrick from the University of Kansas summarized the situation. JWST is not just tweaking our models, it's breaking them. We're in a crisis where our most successful cosmological theory conflicts with direct observations. The Lambda-CDM model isn't wrong about everything. It still explains the cosmic microwave background beautifully, but something is missing. Some physics we don't understand operated in the early universe. Maybe dark matter behaves differently at high densities or temperatures. Maybe there's a fifth fundamental force we haven't discovered. Maybe the universe underwent a phase transition that accelerated structure formation. Or maybe, and this is the most radical possibility, the Big Bang itself was different than we thought. JWST's mission is expected to last 10 to 20 years. We're only 2 years into its observations. Upcoming observations will target deeper fields. JWST will observe even smaller patches of sky for even longer periods, detecting galaxies at redshift Z equals 20 or higher, just 180 million years after the Big Bang. If massive galaxies exist there too, the crisis deepens. Spectroscopic surveys. Many galaxy candidates await spectroscopic confirmation. JWST's spectrographs will measure precise redshifts and compositions for thousands of early galaxies. First stars search. JWST will continue searching for population 3 stars. Finding them, or definitively proving they don't exist, will constrain early star formation models. Gravitational lensing. Using massive galaxy clusters as natural magnifying glasses, JWST will study galaxies too faint to see directly, probing even earlier epochs. What should we expect as JWST continues observing? Conservative prediction: current observations represent rare, unusual galaxies that formed in special circumstances, dense regions, unusual initial conditions. Deeper surveys will show most early galaxies match predictions. Radical prediction: the pattern continues. The more JWST observes, the more it conflicts with Lambda-CDM. We'll need fundamentally new physics to explain the early universe. Dr. Paul Sutter, astrophysicist and science communicator, offers a third option. Maybe the universe is telling us that our entire picture of cosmic history needs revision, not just tweaks to models, but a paradigm shift comparable to when we discovered dark energy. Recent breakthroughs in 2024 suggest this might be the case. In March 2024, JWST detected galaxies at redshift Z equals 14, showing mature stellar populations with ages of 300 to 400 million years, but they exist only 280 million years after the Big Bang. The math is impossible. These stars formed before the universe existed. Unless our dating methods are wrong, unless redshift doesn't mean what we think it means, unless the Big Bang happened earlier than 13.8 billion years ago. Some physicists are now proposing radical alternatives to the Big Bang model. Tired light theory. What if redshift doesn't come from cosmic expansion, but from light losing energy as it travels vast distances? This would mean distant galaxies aren't actually ancient, they're just far away. Tired light was debunked decades ago because it conflicts with cosmic microwave background observations. But some scientists are reconsidering variants that might explain JWST data. Cyclical universe. What if the Big Bang wasn't the beginning, but just the latest in an infinite cycle of expansion and contraction? The ancient galaxies JWST sees might be remnants from a previous cosmic cycle. Dr. Roger Penrose has proposed this model, though it remains highly speculative. Modified gravity. What if gravity behaves differently on cosmic scales than Einstein's general relativity predicts? Modified gravity theories like MOND, modified Newtonian dynamics, could affect structure formation rates. Quantum cosmology. What if quantum effects in the first moments after the Big Bang produced a fundamentally different early universe than classical models predict? These are speculative. Most cosmologists still believe Lambda-CDM is fundamentally correct and needs refinement rather than replacement. But JWST is making the case for radical alternatives stronger with every new observation. The universe, it turns out, doesn't care what we believe. It simply is what it is. And JWST is showing us that what it is differs dramatically from what we thought. If JWST's observations hold up, one possibility is stark. The universe is older than 13.8 billion years. The 13.8 billion year figure comes from cosmic microwave background measurements combined with Lambda-CDM model assumptions. If the model is wrong, the age calculation is wrong. Some alternative models suggest the universe could be 15 to 20 billion years old, giving galaxies more time to form and mature. But this creates new problems. Stars exist with measured ages that calibrate well with 13.8 billion years. Changing the universe's age requires recalibrating stellar evolution models, nuclear reaction rates, and cosmological distances. It's not impossible, just difficult. And it raises the question, if we're wrong about the universe's age, what else are we wrong about? Here's a deeper puzzle. Why does the universe produce structures at exactly the rate needed for life to evolve? If galaxies formed much faster or much slower, the conditions for life would be different. Too fast, and stars burn out before planets can develop life. Too slow, and the universe would be mostly empty when life tries to emerge. We observe structure formation at a rate that allowed solar systems like ours to form roughly 9 billion years after the Big Bang, plenty of time for complex chemistry to develop in earlier stellar generations, but not so long that the universe has expanded into cold emptiness. This fine-tuning has always been mysterious. JWST makes it more mysterious by showing that structure formation was even more precisely calibrated than we thought. Is this coincidence? Anthropic selection in a multiverse? Evidence of design? These questions extend beyond physics into philosophy. If our cosmological models are fundamentally wrong, if the universe doesn't work the way we thought, how many other aspects of reality do we misunderstand? Some physicists have suggested that the universe's unexpected properties might be evidence for simulation. If reality is a computed simulation, the code might have shortcuts or optimizations that look like physical laws to us. Early structure formation could be such a shortcut. The simulation initializes with mature galaxies rather than computing the full formation history. This is speculative to the point of philosophy, but JWST's observations raise the stakes for these discussions. Dr. David Kipping from Columbia, who studies the simulation hypothesis scientifically, notes, "When observations consistently conflict with our best theories, we have three options: revise the theories, question the observations, or question the underlying assumptions about reality itself." JWST forces us to consider all three. The most profound implications emerge when we consider whether our universe is older than we think, governed by different physics than we understand, one universe among many in a multiverse, or something even stranger than our current frameworks can't capture. JWST isn't just revealing distant galaxies, it's revealing the limits of human knowledge itself. Massive galaxies formed impossibly early. Supermassive black holes grew impossibly fast. Structure emerged impossibly quickly. And the patterns JWST reveals challenge the very foundations of cosmology. The evidence is undeniable. These observations are real, replicated, and growing more detailed with every passing month. What they mean remains uncertain. Are we witnessing the death of the Lambda-CDM model? The birth of a new cosmological paradigm? The discovery that the universe is older, larger, or stranger than we imagined? Or are we simply seeing the universe as it truly is for the first time, unfiltered by the limitations of previous instruments? The search for answers continues. Every week, JWST releases new observations. Each one adds detail to our understanding or reveals new mysteries. Theoretical physicists are working overtime, developing new models, testing new ideas, challenging old assumptions. Future telescopes will push even deeper. The next generation of ground-based instruments, the Extremely Large Telescope, the Giant Magellan Telescope, will provide complementary observations in visible and near-infrared wavelengths. And eventually, perhaps in the 2030s or 2040s, humanity will build an even more powerful space telescope capable of answering the questions JWST has raised. But for now, we live in a moment of cosmic revelation. JWST has pulled back the curtain on the early universe, and what we see challenges everything. The universe is vast, the mysteries are endless, the journey continues. And somewhere in the depths of space, 13 billion light-years away, ancient galaxies shine with light that left them when the cosmos was young. Galaxies that shouldn't exist, but do. Impossible galaxies in an impossible universe. And we're only just beginning to understand what that impossibility means.